the light is change, we have to use HSI model, but for example in some applications such as segmentation in the image, we can use or we have to use RGB color space. We will talk about this later, and I will show you some example, and then you better understand that why we have to use the RGB color space instead of HSI or CMY in the segmentation. But before that, first I would like to talk about the pseudo color image processing. It means that we want to assign the color to the different gray level or gray level scale. We will assign some value to find some colors to find the better result. And you can see, for example, if we consider this axis as a gray level axis, starting from black, that is equal to 0 to L minus 5, and we call it a slicing plan that we call, for example, in this shape, we can use it as a P. When we move the plane in this axis, we can see we have the, for example, if consider that here we have some part that it's divided by this plane, slicing plane, that then for each part or which for each gray level scale, we assign a color. For example, if we use 8 color for each gray level, for example, in this image you can see the monochrome image that we just have a color in the image. You can see we can't except, for example, these parts we can see any changing in the image, but when we assign a color to each gray level scale, we can find this shape from this. As you can see, we just used 8 colors, and you can see, for example, here is another area that in this image we think that it's the same, this part and this part, but you can see that we have different area, this, but in this image we can use it. And it's usually this technique is used in the medical image processing to detect some tumor or some cyst in the body or brain or something like this. And also you can see that we have a monochrome image here. When we assign some colors in this image, we assign 256 colors to the monochrome image in each gray level that we have in the image. For example, you can see in this area, in this image, we can see that there is some differences, for example, in this area, but when we assign some colors, you can see that we have other colors here. That it means that we have different gray level in the image. And also you can see we add some 256 color to this image. And if we zoom in the part of the South America region, here you can see that, for example, here we hardly can detect that the value here are different, but here we can easily see that the value are different, because for each grade level we assigned a color, and you know that we have the light green here and dark green here and some black lines here. Also you can see that also for the satellite images we can use this technique that we call it pseudo color, or assigning color to the gray level. It's another application of this technique. And I mentioned before, for the RGB image, we have to transform a gray level or grayscale image to the R here by using a function, transformation function, to the green and also to the blue. And then after that, after add this image or this function together, we can easily generate the RGB color image. It means that, for example, if you read a color image in the MATLAB, you with hyperbolicity, or not, but it depends on the image, but with hyperbolicity, for example, you can see that the value of the size of the matrix is equal to, for example, 255 multiplied 3. It means that it's in the we have the color image, but if you convert the image to the grayscale, color image to the grayscale, and then you can see that, for example, the size of the matrix is equal to 255, for example, 255. It means that we just have two-dimensional matrix that is the gray scale, and we have this in color. Okay? And what does it mean at 3? It means that we have the matrix of 255 in red, 255 in green, and 255 to blue. Okay, then for example, this pixel, if we consider as the first pixel, if the value of the, for example, 100, 150, 200, after combining this matrices together, we can we easily find the a new color. That is a combination of the blue, green, and the red. But when we want to find the color image, we have to use some transformation function. For example, the function that we use in the pseudo color in the technique that we talked about this. And also you can, for example, see for this image, we have the axis of the, for example, if you consider that this, the axis from the 0 to L minus 1, also L minus 1, that we have the gray level. Here we have the red like this, green like this, and blue like this. We can easily find that, for example, in this area, or for example, when we have this, we have the blue. For example, in this area, we can see that the weight of the blue and the green are more than the red one, because the red is here. It means the value of the red is less than the green and blue, and you can see that we have the blue color here, and sometimes that, for example, for the background of the image, for example, here, yeah, you can see that we have the red color. We can say that the value of the red in this area, it is more than the value of the green and the blue. But although that we know that we have some blue color or green color in this area, but the weight of the red color is more than the other colors that we use. And also sometimes you want to apply some filter, or you want to work on the RGB color image, in general we want to work on the color image. There are two ways that you can use this. For example, if you want to assign some mask or some filter for any reason, smoothing, sharpening, or something like this, you can apply the mask, for example, special mask to each component. It means that RGB, or you can separately, you have to apply on them, or you can consider the value of the RGB as a vector. Here you can see, for example, this is the value of the R, this is the value of the G, this is the value of the B as a vector, and after that apply the, for example, filter or mask on the RGB color image. And also you know that, as you remember when we talked about the grayscale image, we just use a mask on the image that go from, for example, here to here, and we use this mask for some purposes such as smoothing or sharpening. And also you know that, for example, when we have the RGB, we have to consider it as a vector. That usually most of the application they use this technique instead of to apply the mask on the R. For example, if you consider this as an R, you can you can apply the filter just on the red, and then after that green, and after that blue. But most of the application they consider this value as a vector, and then apply the filter or mask on the these vectors. Also, you can see some example of the different color space and the different component. For example, if you see that we have the full color image here, when we transfer it to the cyan, magenta, and yellow component, we have the cyan, this like this, magenta and yellow. And also when we have them in the RGB, as you can see easily that, for example, because the strawberries are in the red, you can see here strawberries are in the red, it's more visible to us to, for example, count the strawberries instead of, for example, here or here or also here, because you know that most of the color in the strawberries are red and it's more visible. And also we can, if we transfer this image to the HSI color space, you can see we have these these components that it's like the grayscale image. It means that if you just convert this color image to the grayscale image, you easily find this. But we can't say that this is the grayscale, because it's in this part, in this area, it's a part of the space, or it's a part of the model. But we can assume that this is the gray scale image. And another technique that we can use is the color complements. It means that we have the complement for each red, or we can also call it color inverse. it means that, for example, the text, for example, in these colors, if we assume that this is the cyan color, it's more visible, for example here, if you consider this, it's more visible in the background of the red. It's just an example of this. It means that it's the complement of each other, cyan and, for example, the red. If we turn this vector in this direction, you can see, for example, magenta, it's the inverse of the green. That means that, for example, when we have the text in the green, it's more visible in the background of the magenta instead of the, for example, background of the yellow. But we have to know this when we want to assign some colors to the image. For example, you know that the image, for example, from 50 years ago, all the image was in the grayscale. We didn't have any color image. But you know that with some techniques we can easily assign some colors to the gray level. For example, one of the technique that's the soda color. But on that technique, we have to know that when we want to assign some colors to, for example, to the hair of the people, we have to know that what's the background of this. But because maybe sometimes we, for example, assign some the black color, the hair of the people, and also the background of the black. Means that it's will lost on the color, the background color. We have to know this, that each color has the inverse in this circle, if we use as a color circle. Also, you can see that when we want to find the inverse of the image, for example, if you consider this as an RGB image, that we have this, we just have to change the colors in the H value, in the H matrices, because we know that the colors that we have in the image, it's just in the hue matrices. You know that for the, remember that for the saturation, we have in the saturation matrix, we know that how much of the colors that are in the H are in the image. But when we want to find the inverse, we have to change the value of the H, because, for example, if we move this value in this area, for example, red to magenta, we have to move this part, because it's the circle. It moves to the green part. It means that the colors will change, not the value of the color in the image. We just change the color, for example, from red to magenta, not for example, the value of the red or to value of the magenta. And it's the reason that why the hue matrix will change instead of the saturation matrix and intensity matrix, because we know that intensity matrix is just the gray level of the image. And know that we can see here if we complement RGB component. For example, here you know that's the red, and we remember that the red, the complement of the red is cyan, and you can see that we have the cyan color in the strawberries here, and also for the light green here. If we consider, for example, light green here or here, we can easily just find the complement or inverse of this, for example, here, and if you consider this for the light color, light green, we have to after the applying the complement or inverse of the color, we have the colors like this. And also you can see we have some magenta color here, and it's the inverse, it's the complement RGB component inverse of this, and it's there in the HSI. And also you can see that we have the actually it's we have the same image, but not exact the same color, but not exactly, but are very close to each other. And it's used by using some complementary color techniques. And also, as you remember, when we talked in the image enhancement in the spatial domain, we talked about some filters such as average filter that used for smoothing, some Laplacian filters that used for the sharpening, but exactly the same story in the grayscale image are used for the color image. That, for example, we can use for smoothing, we can use the average filter, and for the sharpening we can use Laplacian filter. You remember that, for example, for the grayscale image, when we want to apply the average filter, we had the function like this. But when we want to use this filter in the color image, we just, as remember I mentioned that just use it for the R matrix or R image, that's the red image, the green and the blue, and after that we can use the smooth image. And also for the Laplacian or sharpening filter, we can use this. As you remember, we had exactly function or equation for the similar to this for the grayscale, but instead of the three color, we just had one color that was the grayscale. But here also for the sharpening, we have to use this. It means that we have to filter on the red matrix, green matrix, and blue matrix. Then after that we can find the sharper image. As an example, we can use, for example, this. We can see that we have the full color RGB image. It's the Lena image. It's the Lena image in R. Means that the green and the blue value are equal to 0. All the pixels are equal to 0, but just the red matrix has some values for its pixel. And also for the green matrix, it means that, for example, here, as you remember, for example, when we want to have just the image in the green, in the red, all pixels, the value of all pixels are equal to 0, and also for the blue matrix, all values is equal to 0, and we just have some values here for the green, but different value. For example, 150 here, maybe 25, maybe 28 for the other values. And also you can see we have the green image here, and also blue image here. As you can see, because the tone of the colors are close to the red in this image, we can see easily more visible image rather than, for example, the blue image. And also, if we convert this image, RGB image, to the HSI, easily you can see that the colors that we have in this image, for example, these colors that we have, these colors, and also saturation image, that we say that how much of the colors we have this, and intensity image, that easily we can say it's the grayscale image of the RGB image. If you want to assign a smoothing filter, such as for example averaging filter that we use for the smoothing, it's the original image. No, excuse me. This is the original image. This is the image after applying the smoothing by 5x5 averaging mask in the RGB RGB color space. You can see we have a smoother image rather than this, and it's the after applying the filter in the I component of the HSI filter. Do you know what happens if we apply the filter on the hue component or the intensity component of the image? Do you know what happened to the image? For example, here we apply the filter on the intensity component on this color space. But what happens if we apply the filter on H, for example, hue component of the image? Do you know what happened?
The color changes.
Yeah, it means that the color will change, and we destroyed all the image, because you know that the hue components include of the all the colors, and when we want to apply the smoothing filter, we want to work on the edges and some details of the image. We don't want to change any color in the image, because we want to use a smoothing image. We don't want to change the colors. It means that we must apply the smoothing filter on the eye components that we can see here. We have all details of the image here. If we apply this the filter on this, we can easily just smooth the edges and details here, but we don't want to change the colors, or for example in the saturation we don't want to change the weighted of the colors in the image. And also with hyperbola maybe you can see it. It's the difference of this image after applying the RGB image, and after applying the smoothing image on RGB color space and HSI color space. The difference, you can see we have some edges here, and also if we apply a sharpening Laplacian filter, sharpening Laplacian mask on the image, you can easily see that we have sharper details instead of, for example, here that we have some smoothing. Here we can see the result after applying the Laplacian filter on the RGB color space, and also after applying the Laplacian filter on the intensity component of the HSI. And also you can see the difference between this image, and also you can easily see that the more details are visible here rather than this, because in this part, in this image, we just use a smoothing. It means that we smooth the edges and details in the image. Another technique that earlier I mentioned before is the segmentation on the image that is usually used for the medical image processing, and also you have to use it in the RGB color, because we want to find the distance between the center and the value of the color that we have. This we can find easily the distance by this equation. You don't need to memorize this, and because you don't ask it for the your exam, but for your information you can use this to find this equation to find the Euclidean distance. between the Z and A when the A is the average RGB vector and the Z arbitrary point in the RGB space. And we can segment it by using this. It means that if you want to show an example here, after the, for example, if we consider this image, we want to segment this area that we call it area of interest. First, we have to find the area of the interest. Then we have to find the mean RGB value, RGB components, and a standard deviation value of this. We have to find these values, and you easily find this because we talked about this last week and 2 weeks ago. And then after defining the D0, that's for the standard deviation of the sigma. For example, for the D0, for the matrix of the R, red we have the 1.25 sigma R. Also for the green and value. This value is just for this image. We can't say that it will use for the other image. And then any pixel within D0 distance from the mean is set to white color. That is the region of interest that easily we can see this. And all the other pixels are set as a black color. It means that we have to find the distance and put 0 or 1 or 255 to segment this area of the image from the rest, because maybe in this area we have some problem. But you don't need to memorize this part, it's just for your information, and we can easily segment this region. That's the reason that why we have to use in the RGB, because we have to find the standard deviation of each value. If we use it in the HSI component, we can't use the standard deviation of the hue, saturation and intensity, because you know that for the hue we have the colors and the I, for example, it's the gray scale or intensity of the image. And that was the topic that I had planned to talk about this. It was the color image processing. And that's it. Do you have any question about this? If you don't have any questions, the last of this lecture, the end of this lecture, and remember that 10 minutes before the class I upload the third homework, and you have 2 weeks time to